Hello everyone, and welcome to our 10.6 notes on segment relationships in circles. The first theorem that we're going to look at is our intersecting chords theorem. And so the intersecting chords theorem states that when two chords of a circle intersect within the circle, so let's slow down and look at that first. We have two chords intersecting. Remember that a chord has its endpoints on the circle. So that green chord is intersecting this blue chord. So when they intersect, they cross at a point. The product of the segments of one chord is equal to the product of the segments of the other chord, meaning that C, this little piece, C times D, is going to be equal to A times B. Those smaller segments are going to be equal to each other. So you take the product of C and D, C times D, is going to be equal to the product of A times B. So let's look at why this is true first. You know, I always want you to look at the why behind a theorem. Why does the intersecting chords theorem work? Well, whenever you have a circle and you have intersecting chords, we can create these triangles on this circle. And so we get to add vertical angles. We know that one is obviously bigger than the other, so they're not congruent. But I get to add that the vertical angles are congruent. And then I also get to add that these angles are congruent, this red one and this red one. If you think back to what we've just learned, sorry y'all. Okay, there we go. If you think back to what we just learned, both of those angles, those inscribed angles, open up to the exact same arc. And so since both of those open up to the exact same arc, those angles must be congruent to each other. So now we can say that these triangles are similar by angle-angle similarity. By AA similarity, these triangles are similar, so all the lengths have to be proportional. So let's look at that. We know that the proportion of C over B should be equal to the proportion of A over D. A over D. We're going left to right and left to right. And so whenever we do that, that is proportional. Those two ratios should be equal. And so when you go to solve that and you cross multiply, C times D is going to end up being equal to A times B. And that is exactly what our intersecting chords theorem says. The product of those pieces are going to be equal. And so if you had somebody that just roughly measured the pieces of a chord, the segments of each of these chords, it says these measurements have been estimated. So I'm going to underline that. So we want to see how precise they were. How good of a job did they do measuring? Well, if they did a really good job, then their products should be equal if they're precise. If they're estimated, we know that they should be close. So if they went through and they measured this segment using a ruler and they said, hey, this is about 50. Well, what is the other segment on that same chord? That's going to be 50 times 148. That should be really, really close to, if not equal to, if they measured well, 71 times 104. So let's see how close they were. 71 times 104. So 50 times 148 is going to give me 7,400. And 71 times 104 is going to give me 7,384. So we can tell that they've been estimated. Those are not exact because those would be equal to each other if they had measured exactly. Okay, so pretty close. But in general, whenever you have this theorem, the products are always going to be equal, okay? The exact products are going to be equal of those lengths. So then we have something else called the intersecting secants theorem. So let's look at this other theorem. The intersecting secants theorem talks about whenever you have two secants intersecting. Okay, so let's look at this. We've got our blue secant that touches the circle twice, both here and here. We've got this green secant that touches this circle twice, intersects this circle twice, both here and here. And these two secants are intersecting outside of this circle. And so we've actually learned a few theorems about this already with the angles, but now we're learning theorems about the actual pieces of the secants themselves, so the actual segments on these chords. Here's what it says. It says that the product of A times B is going to be equal to the product of C times D. So here's another way that I write that. A is from the point of intersection to the circle, so that's going to be the outside piece, times the whole thing from the point of intersection all the way to the point of intersection with the second time it touches the circle. So the outside times the whole is going to be equal to the outside, which is just point C from here to here, that first point of intersection, the outside, times the whole as well. C all the way to This point would be to D. That point would be, we're calling that length D, so that's the outside times the whole. Okay, so A times B, outside times whole, is going to be equal to the outside times the whole. And when I say whole, I mean from the point of intersection to the second point of intersection of the circle, the big one, and then the outside is just the point of intersection, the outside of the circle, to where it meets the circle for the first time at that first secant point, where it touches it. Okay, so outside times whole is equal to outside times whole. A times B is equal to C times D. So it says again, these measurements have been estimated. So let's see how close they are. So 12 times 25, if they did a good job measuring, should be very, very close to 13 times 23. So outside times whole is equal to outside times whole. Let's see how close they were. 12 times 25 is 300. That's going to be 300. What is 13 times 23? 299. So this person did a very, very good job measuring. Now they're not exact. So you can see that they've been estimated. If they had measured exactly, then you would have the exact same products there. Okay. It says that this line doesn't only work for two secants. It also works if one or both of the lines are tangents. But since we don't have an inside and an outside of a tangent, we write c squared. So let's look at this. On this blue secant line, I do in fact have an outside. I do, in fact, have a whole. So that's still outside times whole. Outside times whole. Okay? But look at what happens on the other side. What is the whole thing for our green line? The whole thing is C. What is the outside? Well, the whole thing is outside. So whenever you set that equal to outside times whole, that ends up getting multiplied by itself. So it's still outside times whole equals outside times whole. It's just that C is both the outside and the whole. And so when you do C times C, that gives me C squared. Okay. All right, so let's do a few problems. It says solve for the indicated value, round to the nearest tenth if necessary. So rounding to the nearest tenth. Okay. All right, so what we're going to do here is we are going to use our very first theorem that we called the intersecting chords theorem. Okay, so we have two chords intersecting. And what do we know about those intersecting chords? We know that the products of those segments should be equal. So let's just make sure we're picking the right ones. The 6 goes with the yellow piece. The 5 goes with the other segment in that yellow chord. So 6 times 5 should be equal to what? It should be equal to x times 8. X times 8. X times 8. Okay, well 6 times 5, we know that that is just 30. What is 8x times 8? We can rewrite that as 8x if we want to. So I'm going to divide 30 by 8, and that is going to give me 3.75. X would have to be 3.75. Exactly, for those to have an equal product. So we were able to find unknown pieces of segments of chords using this theorem. Okay, let's do this again. We've got this pink chord intersecting this yellow chord. So I can set those pink pieces, both 9 and x minus 3. 9 times, I'm going to put that in parentheses because there's two pieces. 9 times x minus 3 is going to be equal to 10 times 18. So remember, this turns into the distributive property. I'm going to distribute the 9 to both the x and the 3. So that's 9x minus 27 is going to be equal to 10 times 18, which is 180. I'm going to add 27 to both sides, and then I'm going to divide by 9. That is going to give me, for x, my value would have to be 23. Let's check that real quick. If we plug that in, that would be 23 minus 3, which is 20. Is 20 times 9 the same thing as 10 times 18? It is. Both of those would give me a product of 180. So those products would be equal. All right, now we have a secant and a tangent intersecting outside of the circle. So they're crossing outside of the circle. So we've got two pieces that get created. We have an outside and a whole. And then we have, on this problem, we also have an outside and we have a whole. But let's see what happens when we set that up. So we're going to take our outside and we're going to multiply by our whole. So our outside piece is 8. What is the whole thing? Well, we're going to have to add that 16 and that 8 together. So I'm actually going to give myself a little bit of room. So here is 8. 8 is my outside piece. What is the whole thing? It's going to be 16 plus 8. Well, what does 16 plus 8 give me? 16 plus 8 is going to give me 24. So I'm going to do 8 times 24, outside times whole, is equal to the outside piece, which is z, times the whole thing, which is also z, because that's tangent, z times z. And we know that z times z gives me z squared. So what is 8 times 24? 8 times 24 is 192. 192 is going to be equal to z squared. Well, if that is what z squared is equal to, how do we get what z is equal to? We do the inverse operation, which is taking the square root. What is the square root of 192? It's going to be equal to exactly the square root of 192, which is about 13.9 if we rounded it. Round to the nearest tenth if necessary, so we did have to round that up. Okay? All right, let's look at a few more problems. Let's keep doing this with our secant. This is our secant. Okay? So we have our outside times our whole is equal to our outside times our whole. So what is the outside of the green piece? Just from the point of intersection to the first circle, that is going to be 3. Times what is, so 3 times what is the whole thing? That whole thing is going to give me 8. So outside times whole, 3 times 8, should be equal to the product of the outside piece from this point of intersection to the circle is 4. That's the outside. Times what is the whole thing? The whole thing, let's see, from here all the way to here is going to be 4 plus x. 4 plus x is that whole thing. So we had to add it together. So again, this is going to be some distributive property. I'm going to have to distribute the 4 here and here. Outside times whole is equal to the outside times the whole. So what is 3 times 8? That is 24. What is 4 times 4 plus x? That is going to be 16 plus 4x. And so we're going to get 4x equals 8 when we move the 16 to the other side by subtracting. And when we divide by 2, that is going to end up giving me 2 for x. You could go back and plug it in. 3 times 8 is 24. 4 times 6 is 24 as well. Okay, so I know that I did good work on that one. All right, so now we have, what is this one? We have 2 secants on this problem. Okay, we've got secant and we've got a secant. And so we're going to do the outside piece, which is 6, times the whole thing. What is the whole thing? That is going to give me 6 plus 8, which is 14. Outside times whole. 6 times 14 should be equal to 7, the outside piece, times the whole thing. Well, what is the whole thing? The whole thing is going to be 7 plus y if we add those together. So again, this is going to be some distributive property. I'm going to distribute the 7 to both of these pieces. 6 times 14 is going to give me 84. 84 is going to be equal to 49 plus 7y. So we're going to subtract 49 from both sides. And then we're going to divide by 7, and you're going to get 5 for y. Y is equal to 5. Go back and check that. 7 times, let's see, so 7 times that whole thing would be 12. 7 times 12 gives me 84, and then 6 times 14 gave me 84 as well. All right, let's do this again, but this time we have a tangent and a secant. So we've got 4, which is the outside, times the whole thing. Well, what's the whole thing? We're going to get an expression, an algebraic expression. 3x plus 4 would be that whole thing. 4 times 3x plus 4 is going to be equal to the outside, which is 8, times the whole thing, which is also 8. So that ends up being that squared, 8 times 8. Then we're going to use our distributive property. That's going to give me 12x plus 16 is going to be equal to 8 times 8 is 64. So we're going to do 64 minus 16 divided by 12. So what is x? X is going to be equal to 4. Okay. All right, the last 2 problems, these look a little bit scary, but they really aren't. We're eventually going to try to find the diameter in this problem. So since I'm looking for the diameter, that is a chord. Remember, a chord, all diameters are chords, not all chords are diameters. So a diameter is just a chord that goes through the center of the circle, which is point O. So I'm going to call that x. So this is still just a secant and a tangent. So my blue one is my tangent. And then my pink one is going to be my secant in a second. So so the blue goes from here all the way to here. So let me highlight that in a different color. Let's go yellow. That's going to be from here all the way to here. Okay. So what is our outside of the yellow? Our outside of the yellow is 12. I'm going to have some space here. The outside of the yellow is 12. What is the whole thing for the yellow? It's going to give me an algebraic expression of 12 plus x. 12 times the whole thing, 12 plus x, should be equal to the outside piece, 24, times the whole thing, which is also 24. So I'm going to use some distributive property here. 12 times 12 is 144, plus 12x is going to be equal to 24, or 24 squared. 24 squared is 576. You could also have just done 24 times 24. Okay, so I'm going to take 576, I'm going to subtract 144, and then I'm going to divide by 12. And I end up getting that x is going to be equal to, write that down here, x is equal to 36. X is equal to 36. So we were able to find that missing piece, which is the diameter, by using a variable, and then we just found what x was. And then you could check that. If you did 12 times, let's do 36 plus 12 is going to give me 48. So 12 times 48 is also going to give me 576. So I know that I did that problem correctly. Okay, last one. We want to find the diameter. Well, which one is the diameter? The diameter is the whole thing, so I'm going to highlight that in pink. But we have a piece of it. We have a piece of it is 3. So what would the other segment be? Well, we don't have a variable there, but I'm going to put one. From here all the way to here is x. And then what we have is we have a chord from here to here that is getting cut in half by this diameter at a 90-degree angle. So that is going, if this side is 4, this side is also going to be 4. So what we're going to do is we're going to set 4 times 4, that product, equal to 3 times x. So what is 4 times 4? 4 times 4 is 16. That is going to be equal to 3x. And you're going to take 16 and you're going to divide by 3. That's going to give you 5.3 repeating. So x is equal to 5.3 repeating. Okay, that's what x is, but we want to know what our diameter is. So our diameter is going to be 5.3 repeating plus 3, which is going to give me 8.3 repeating. I think that they did tell me to round to the nearest tenth, so that would be about 8.3. Okay, exactly 8.3 repeating, or 8 1/3, but it is 8.3 rounded. So we have our what it's equal to, and then what it rounds to, our equal sign and our approximately sign. So you have some practice on those two theorems with these next 9 problems, and we will check those tomorrow.